Hey guys, today we continue our discussion on non-renewable energy resources. We're looking at fossil fuels, specifically natural gas. Natural gas is a mixture of gases of which 50 to 90% is methane. Methane is the simplest hydrocarbon. It is one carbon atom bound at the hips with 4 hydrogen atoms. Now, there's actually both renewable and non-renewable methane. This lesson is meant to focus on the non-renewable. Eventually, however, we will refer to renewable methane, which is what we call biomass. And this is created from the decay of organic material in the absence of oxygen. So anaerobic decomposition in landfills, sewage treatment plants, and cattle waste and flatulence all produce renewable methane that's regenerated on a human timescale. What we're looking at is the material that is not generated on a human timescale. Conventional natural gas forms usually alongside or above the formation of oil. So to form that, we have to go way back into those prehistoric seas where eutrophication creates massive algal blooms. That organic material sinks to the bottom of the ocean where it accumulates to form a stinky source rock material, shale, rich in organic material. It has to cook. And like we said, it has a very precise cook time to form oil. And when you overcook it, that's when you get natural gas. So more often than not, when we have a petroleum deposit, right above it usually sits a natural gas or a methane deposit. The largest reserves of natural gas, the Saudi Arabia of natural gas, is actually Russia at just under 25%, followed by Iran. The United States has less than 5% of the conventional natural gas, yet we use quite a bit of it, 22% of the world's production. And I think the reason why we're starting to increase the production is because of that ample supply. Its versatility, so it's commonly used to heat our homes, for electricity. It can actually even be used to propel our vehicles. That ample supply results in a high net energy yield, and many analysts argue it's sort of a way out of our polluting energy and perhaps a solution to a more sustainable energy future as we begin to transition into renewables. Remember, it releases far less carbon emissions, less than half the amount compared to coal, and less than oil, of course. So it doesn't contribute nearly as much to global warming. Furthermore, it burns much cleaner. 1/10 of the amount of pollutants is given off from natural gas compared to coal. That's because it's a gas and it burns more complete. There are disadvantages of natural gas, of course. Many deposits are located in fairly remote areas, and without infrastructure such as pipelines, it's really difficult to transport. So as you can imagine, in this oil rig offshore, oftentimes that methane is just vented and burned off. It's burned off because, well, they don't want to release the methane into the atmosphere, because compared to carbon dioxide, methane is far more potent as a greenhouse gas. It's 25 times more potent. So it makes sense just to burn the methane, and that gets converted into carbon dioxide. If they did want to transport it from a more remote location, they have to liquefy it. They put it under intense pressure and low temperatures, and that liquefies it, and they transport it, which can be somewhat dangerous because it's combustible. And then when it gets to port, it gets warmed up and converted back to a gas. You can imagine all of that requires a lot of energy, and therefore it lowers the net energy yield. Methane is a really potent greenhouse gas, as we mentioned, And when we combust it, it releases carbon dioxide. To be fair, far less than coal and oil, but it still releases greenhouse gases. In addition to the conventional natural gas, we also have unconventional natural gas, and it has allowed the United States to become the world leader in natural gas production. One major source of natural gas is the methane that's typically associated with large shale deposits. That is sort of the uncooked or not properly cooked source material that was never converted to oil. It turns out the United States has large deposits of shale that has a lot of natural gas. In fact, the Marcellus Shale Formation that resides in southern New York and extends through Pennsylvania and West Virginia is estimated to have 500 trillion cubic feet of natural gas. The way in which we actually extract that natural gas is through a process that's somewhat controversial, known as hydrologic fracturing. They use water and they pump it into the shale formation, sometimes over 7,000 miles deep. Excuse me, feet, of course. And they inject that water deep within the crust. It creates these cracks or fissures in the shale. Now, those cracks and fissures allow the methane in that shale to emanate, and then it uses the pipeline as a conduit in which the gas is then pumped back to the surface. Now, in order to keep those cracks open, not only do they use water, but they also pump sediment, sand, as well as various chemicals to sort of lubricate this process and keep the cracks propped open so that the methane can continue to flow out of the cracks and into the pipeline. Some of the chemicals and the chemical cocktails they use include benzene and formaldehyde. Benzene is a known carcinogen. And so we're very concerned that some of these fracking fluids will leak from this pipeline. And as you notice, these pipelines pass right through aquifers, which can certainly contaminate our drinking water. Other unconventional sources of methane include coal seams. So methane typically resides in coal. Coal seams are often supersaturated with water. So the water pressure actually holds the methane in the coal. And before coal mining begins, methane is typically released for safety purposes, especially if they're doing subsurface mining. They don't want it to combust, and so they vent it. Well, now before the mining actually begins, they capture some of that methane. So they'll actually drill wells right into the coal seams where they'll pump not only the liquid, but also the natural gas to the surface. The final unconventional source of methane is what we would call a methane hydrate. It's a cage-like lattice of ice inside of which are trapped molecules of methane. If that methane hydrate is either warmed or depressurized, it reverts back to water and natural gas. The uses of this are somewhat speculative still, and it's in the experimental phase, but we're actually getting somewhat concerned that some of these deposits of methane hydrates are starting to be released into the atmosphere, accelerating climate change. Part of the reason why we are so concerned about this is that the methane hydrates location is often found in the Arctic. These methane hydrates, these cage-like ice structures with methane, are often located in the tundra, in the permafrost. So as the Arctic warms, which is where most of the warming on planet Earth is happening, that permafrost begins to melt, and those methane hydrates release the methane into the atmosphere. So the permafrost, as it warms, is contributing to what we call a positive feedback loop. And when I say positive, I don't mean it's a good thing, right? That stable hydrate is now unstable. As the Earth warms because of climate change, more methane is released to the atmosphere. Methane is a potent greenhouse gas that contributes to more warming. More warming means more permafrost melting, meaning more methane will be released. It's a vicious, self-perpetuating positive feedback loop that we're very concerned about in terms of its impact on the rate of climate change. That's it for today, guys. We'll see you soon.